All right, hopefully everybody can see my screen there. So good afternoon, everyone. I'm Sanil, and I'm going to be talking about my work, high performance code generation for graph applications. So in the high performance computing community, many developers take the classical approach to get performance from their application. They originally write their application, in this case, a 1D FFT, completely by hand, including looping information and calls to functions that they themselves would write. They then run their application and recognize in some instances that they don't get nearly the performance that they expected. So then they'll profile their application to quickly determine where the bottleneck of their application is, and then in some instances replace that bottleneck with an external library call to a high performance interface. This high performance library will give significant speed up, but you'll have to have this cost of refactoring large portions of your original application to conform to this new library. However, these libraries could have some compatibility issues as you introduce new libraries and try scaling out your application. So in the previous code snippet, we saw a 1D FFT algorithm that we now want to parallelize across different processors in a processor grid. Well, this will cause an issue when we have to split the data, as the one-dimensional algorithm that we want to parallelize is now in a two-dimensional space. And so this disconnect between the two libraries would mean subpar performance without further refactoring of either of the two libraries in order to be aware of what exactly the other library is doing. However, once you do such a refactoring and make one library aware of the other, you would get significant speedups compared to that lack of understanding. But the addition of the understanding is quite infeasible, as it would result in a combinatorial explosion of either library interface that the library developer would write. So one of the questions you have to ask is, do we always need to call libraries? And the answer is sometimes yes, sometimes no. In some cases, it could be overkill for simple functions. You might not know the library well enough such that it's a challenge to even incorporate it. And then it becomes increasingly difficult as you introduce not just one main library, but 2 or 3 additional libraries that you're trying to all make work in one application. And this could result in performance that isn't consistent as you move into some special corner cases that the library wasn't immediately aware of. So let's instead recast this problem by taking the library itself and treating it as a domain-specific language. So now the library or API defines the basic operations that one can perform. Then the additional parallelization libraries would define how the global and local communication patterns would work within your application. And then this is all sort of wrapped up neatly in a standard language like C or C++, meaning there won't be any major issues from a language perspective. Now we can utilize this DSL consisting of those 3 distinct pieces: the base language, a parallelization framework or technique, and an underlying library, to understand the semantics of the application and find areas of optimization via a specific domain-specific language compiler. The application we have is no longer an application in the traditional sense, but rather a specification. So it'll say what to be done via library calls, but it won't tell you how to do it, and that's where the compiler would come in. Right, so this will open up the compiler to generate high performance implementations that can take advantage of things like data layout, software performance optimizations, and underlying architectures. So really the big picture idea here is developers will use software libraries to write their applications. However, in many cases, these library-based applications will tend to have poor performance, as the library cannot account for all possible use cases. To make matters worse, a traditional compiler will have a hard time optimizing these applications, especially as you move between library calls or across library calls. The compiler just won't be aware of the functions themselves or how the functions might interact with one another. And library developers, as I mentioned before, cannot write all combinations of function calls to account for specific interactions, as that would cause an explosion in the library size. So what this ends up resulting in is, in order to get performance, an application developer would have to write an optimized version by hand instead of using the library that they would prefer to use. So to alleviate this issue of rewriting, we would propose a domain-specific compiler that can understand the library's semantics, allowing for optimization and generation of high-performance kernels that are equivalent to the original computation. So as you can see by this diagram here, our compiler Spiral will understand the operations meanings and generate high-performance variants using techniques one would do by hand. And I'm going to show how we've taken Spiral and done this for the graph processing domain specifically. And just to sort of give some more context here with this diagram, basically, Spiral will understand that we can create an optimized version of two functions and then pass that along to the application and replace those function calls with our more optimized kernel. So the library specification we are optimizing is the GraphBLAS standard, specifically the C++ implementation, the GraphBLAS template library called GBTL. The GraphBLAS API provides users with building blocks for graph applications that are expressed in the language of linear algebra. So as you can see from this formalization table, the API provides these functions to developers, which describe their mathematical description as well as their input and output behavior. The GraphBLAS API also describes this concept of a semi-ring, which is a structure that defines the addition and multiplication operations over a domain, which will be important later on. And we'll go into that in a bit more detail later on. Additionally, we have the GraphBLAS forum, which is a place to provide continuous updates and improvements to the API. And many GraphBLAS implementations, like GBTL, provide reference implementations for popular graph algorithms. In many of the cases for these algorithms, there is more than one way that you can express it using the API. So there will be multiple reference implementations for the same underlying algorithm. And what makes the GraphBLAS API a good target for our work is that our code generation system Spiral is also based in linear algebra, which makes it a sort of a perfect fit to capture and optimize graph applications that utilize this API. Finally, our work GBTLX is an extension of GBTL that performs the pre-processing necessary for actual Spiral code generation. And so this is saying GBTLX is GBTL plus Spiral. So before we get into GBTLX, I do want to quickly discuss the concept of a semi-ring. So as I mentioned before, a semi-ring is an abstract structure that defines the addition and multiplication operations over a domain. So if we use matrix multiplication as a classical example, we know that canonically it takes a row of matrix A and multiplies and sums each element with a column of matrix B. We can generalize the addition and multiplication operations so long as they follow some of these properties that I've shown here, which is associativity, commutativity, and defines how these operations will operate with the 0 and 1 element, which you'd also define in your semi-ring. Now we are able to sort of generalize matrix-matrix multiplication by overriding the addition and multiplication operations with new definitions given to us by the semi-ring. So some examples of these types of semi-rings would be a binary semi-ring, which has the addition as or and multiplication as and the tropical semi-ring, which has the addition as the minimum and the multiplication as addition. And these semi-rings are used frequently in the graph processing community as they're a way to change a computation depending on the semi-ring that's being employed. So if you were to use a tropical semi-ring in a graph processing application, you might be able to get shortest paths instead of a classical matrix multiplication. So now switching back to GBTLX, this is a software system that enables developers to go from an original GBTL application to a high-performance equivalent without the need for a human intervention. The high-level toolflow of GBTLX begins with the user application. And this consists of two files, the problem specification and the main driver. So the problem specification will house these three classes that we see here, the problem, signature, and solver. And the main driver will actually instantiate them to execute the application. So diving into that in a bit more detail, the first major component here of this user application is the problem and the signature. So the problem is responsible for capturing the input and output objects of the program, and it houses those objects in a sort of meta signature class. This class is also responsible for instantiating the random problem instance function. And the purpose of this function is to create a smaller model representation of the input data set that the user is targeting. So this method is used specifically for trace file generation to capture the application's operations quickly and correctly without running the actual data set, as that might be too large to do in a reasonable amount of time. And then this trace file will be passed to our code generation system for analysis. We'll see that a little later on. So as you can see by this example here, we have the function random problem instance in front of us, and we call an external graph generator to create this representative input graph, which we then pass to our signature object. And this will then be called to do the actual trace file generation. The second component then of the user application is this solver class, and it has two methods, semantics and solve. So semantics will actually hold the GBTL operations that are being performed on the problem, while the solve method will act as the execution trigger, either executing the code written in semantics or the generated code by the spiral system, given to us by the spiral system. So basically, semantics is where the user would write the main algorithm that they're trying to perform. So as you can see by this code snippet here, we are doing a graph processing algorithm called triangle counting, which is counting the number of triangles. And the sort of bolded comment there shows the mathematical expression that gives us the number of triangles in a graph. And it's a matrix multiplication where you're also masking that matrix multiplication with the input graph itself. And then you would then reduce that result into your scalar value that would give you the number of triangles of interest. And we organized the user application in this way because we wanted a very extensible system. For a much more complicated problem, having multiple problem and solver objects, this format enables discernible segments for optimization by our code generation system. And once the user application is now completed, the user would then move to the build system and compile their program with our GBTLX interface. So this interface will house the modified versions of the GBTL operations, as well as an internal driver, which is responsible for the computational trace file generation. So when we created the system, we wanted to capture and add functionality to GBTL function calls without modifying the actual underlying library directly. And how we were able to do this is using the C preprocessor and macros. So what these macros will do is allow us to swap GBTL functions with our interface functions that would either print out some additional information or call the original function directly. And this is important because our code generation system will then read in this function call information to understand what exactly the computation is that's being performed. So if we look at this example here, at the bottom of the screen here, we have this macro that we defined called wrapped MXM. And what it'll do is it'll redirect any call to the GBTL MXM with this call to wrapped MXM. And then depending on our compiler flags that we have here, it'll select which version of the function that should actually be performed, which is either printing out some information about the function to our trace file, or calling the function directly for correctness checks or things like that. And this allows our system to conform to a delayed execution model, where after the first input is given, only the final output is received with no inspection of the intermediate results in between. And we don't want to actually materialize any of those intermediates. So this is a way that we get around that. And this is important because it gives it's necessary for accurate code generation by the spiral system. So just to sort of recapture all this, we have this user application where we describe the problem data set that we're after in the algorithm. Then we compile that with our interface. This interface will then execute the internal driver, which will call that random problem instance function, which is our representative problem, and create our computational trace file of the application. Again, this trace file will capture those GBTL operations, and it's using those wrapped functions that we saw. And then the trace file will then be used by the spiral system to produce a high performance variant of the original application. So here's a quick example of what a trace file could look like. And it contains, as you see, the set of operations that are being performed by the system, with the operations important characteristics like inputs, outputs, and masks and things like that. It's important to highlight that some operations also include custom descriptors via our wrapped functions that describe additional properties of the computation that are not inherently obvious. So in this case, the descriptor would say that we have a symmetric matrix and is using only the lower triangle for the actual computation. So meaning we only compute on the elements that are below the main diagonal of the matrix. We also use hex strings for verification of the inputs and outputs as we move from operations that are within the trace file. So this trace file will be parsed by our spiral script, which we see here. And this spiral will be able to understand the underlying properties that are shown in the trace file and generate a high performance variant. And we'll go through how exactly Spiral is able to generate high performance code in the latter half of this talk. But just to sort of talk about it at a high level, we have to first load our graph package and then parse the trace file to see if we understand or Spiral understands the computation being performed. And then if it does, it'll go through a series of transformations to give us a high performance variant of that computation. All right, so just sort of recapture that. So Spiral will go through these sets of transformations and constraint analysis to determine that the set of operations is one that the system would recognize, and then it will generate a high performance algorithm in its place. So for triangle counting, which we've been talking about, we have the subsection here of the generated code. And as you can notice, it also has a pragma for multi-core support through OpenMP. And this is given to the user without direct user modification. So the system will provide that to the generated code for you. You wouldn't have to go into the generated file and place that in yourself. So just to summarize, the GBTLX Toolflow comes in stages that takes a user application written in GBTL and transforms it to a high performance variant without the need for human intervention. So it starts with the user application, where the user defines the problem on the solver and captures the input data set and the algorithm that the user wants to perform. The application will then build with the interface to capture library calls in a trace file to be analyzed. Again, we want to do this trace file generation efficiently, so we're going to use a small representative problem instead of the actual input. This computational trace file is then the input to the Spiral code generator, which will perform transformations to generate a high performance variant of the original computation. And then finally, the generated code would be linked back to the main driver, which will override our solve execution trigger and run the high performance algorithm on the actual input data set as opposed to the random problem instance. So the remainder of this talk will now focus on the yellow code generation box, or how Spiral goes from trace file to high performance code. But at this point, I do want to ask if anyone has any questions about GBTLX and the software flow, you can ask them now. Okay, all right, so we'll move on. So just to quickly give some background on Spiral, our code generation system. It's a mathematical system that takes these mathematical formulations and converts them into code. So if someone wants, high performance code for such an expression, like the one that we saw a few slides ago, and then they want to target a specific architecture, Spiral will provide one such high performance algorithm with proof that the result is what is expected by the user. So the goal of Spiral is to be able to generate these high performance codes for a wide variety of hardware backends, from server processors to different types of architectures like GPUs and FPGAs, as well as low power systems to the largest supercomputers that are available today. And I guess that the beauty of Spiral really is you can write one specification and then sort of change out these targets, and Spiral will be able to do the rest. And it'll hopefully give you good performance for the target of interest. And the way Spiral does this is by having a formal synthesis model that searches a wide space to find the best fit for the specification. In this model, the user simply specifies what constraints are from the hardware side and the formalization from the software or algorithm side. It'll then take those constraints and that extra information, and it'll prune the search space until it's able to identify any matches that keep the characteristics of both sides. So this would include things like I want to use, vector instructions from the hardware side, and I want it to be of this for a matrix of this dimensionality, and Spiral will then choose the appropriate algorithm for that case. So within Spiral, we define a set of traditionally linear transformations that have a high-level representation and break down to their sort of underlying functions. And this allows for descriptions of algorithms in different domains and the fusion of those domains whenever appropriate. And then these expressions can be tagged with various hardware platforms or parallel paradigms, which will enable proper generation of code for the target architecture. And again, this is all neatly wrapped up such that the system would properly break down according to the inputs without the need of the user to provide any additional modifications. So moving now into the graph space, we're going to discuss this example of triangle counting, or counting the exact number of triangles in an input graph. What's nice about this application is that it has many linear algebraic formulations if you express the input graph as an adjacency matrix. So as you can see in this example, we have an input graph with 4 triangles and its equivalent adjacency matrix. So within this adjacency matrix, each row and column represent all possible vertex pairs, and all the non-zero values correspond to valid edges in the input graph. And these edge weights, should they exist, would be placed there. But for this case, because there are no edge weights, we just place a 1. Things to note are the fact that this graph is undirected, which makes it symmetric across the diagonal, and it has a lot of 0 elements, as there are not many edges in the graph itself. Additionally, triangle counting has many different mathematical formulations that all give the same result of the number of triangles. So we show how Spiral goes from one such formulation that is not geared towards performance to a high performance equivalent. Spiral will utilize a series of transformation stages, with each building upon the previous and providing more details than the previous before finally generating the code for the input application. So how exactly does triangle counting work, you might ask? So let's take our original graph and one of the formulations we saw on the previous page, 1/6 trace of a cubed. So if we start with our input graph A, we're first going to compute a square, the results of which are shown here. What this matrix multiplication has done is it has found all the length 2 walks from one node to all its connecting nodes. However, if you just focus on the elements along the diagonal of the matrix, because they're going to themselves, they only have all the outgoing edges from that node. So position 1, 1 for node would have value 2 because there's only 2 outgoing edges from node 1. So now what we do is we take the a squared matrix and we multiply it again with the original matrix, and this gives us our a cubed matrix. And what this has done is now found all length 3 paths from one node to any other node. And now if we again focus our attention on the diagonal elements, we'll see that because we're going from a starting node back to itself, we have found a triangle for that particular node, because a triangle requires 3 lengths and it has to start and end at the same position. So, however, because we have this 3-edge system and it's an undirected graph, we'll have 6 different permutations. So we have overcounted the actual number of triangles by 6 if we were to sum up all the elements along the diagonal. So what we need to do is simply divide the sum of the elements along the diagonal by 6 in order to get the actual number of triangles, which, as we saw, is 4. So I also want to highlight here something that I mentioned previously, where if you were to now change the semi-ring for this matrix multiplication, we could actually get a different result than what we see here. So if we wanted to find the shortest paths from any node to any other node, we could replace the semi-ring, which we use the traditional one here, which is addition is addition, multiplication is multiplication, with the tropical semi-ring, where addition is now the minimum and multiplication is addition. And that's a way to get shortest paths with an input graph like this. And that shows sort of the power and the reason behind utilizing semi-rings. So to get Spiral to generate code for an application like triangle counting, we need to introduce the concept of sparsity. So as we saw in the previous adjacency matrix, and this goes for many graph applications, the input matrix is usually significantly sparse. So as such, rather than store the zero elements, compute over those zero elements, people will just compress the sparse matrix, which will remove the zeros and therefore the need to compute over those zeros. So as you can see from the matrices above, the dense matrix has many zeros, which classifies it as a sparse matrix. And it's then compressed using a compression format like the compressed sparse row format. In this format, the row index, the column index, and the values are stored for the sparse matrix, and it'll result in significant space savings as you go to very, very large matrices. And then in order to find elements in your CSR matrix, you would take the difference between two adjacent row indices and determine how many non-zeros actually exist in that row. Then you would just go over the column array using that difference to get the associated value. So if we take the blue squares there, we know that there are two elements in our first row, and they're at column index positions 1 and 3, and then they have value 5 and 7. So in Spiral, we added support for sparse arrays and matrices, which we parameterize by type, and we also parameterize by the semiring, and that semiring is also parameterized by type. And this is actually a design decision that we made that differs from our overarching library, GraphBLAS, because in GraphBLAS, the semiring is attached to the operation, but we believe it's better to attach the semiring to the data structure that you're computing over rather than the operation, and that's a benefit for the actual code generation process. So in addition to sparsity, Spiral has to recognize patterns of operations in order to generate equivalence. So to do this, Spiral takes the input operations and places them into an internal directed acyclic graph, or DAG, with the inputs being the operation inputs and the outputs being the operation outputs. And it also houses the carrier information, like the semi-rings and the masks and things. So if we see this diagram here, we have our initial mathematical formulation that we're trying to write with the GraphBLAS standard, and that's sort of shown in pseudocode in the middle of the screen. And then that representation will be internally shown in Spiral, but shown pictorially here as this DAG. And it has the inputs that are flowing through and then the actual operations. Once this DAG has been created, Spiral will use pattern matching and table lookups to see if this sequence of operations is actually known to the system. If that is the case, it'll then produce an initial SPL formulation for this set of operations. So going back to this example, we know we are performing triangle counting with the traditional semi-ring over the integers. So we're going to get a formulation like this, which is triangle count with this arithmetic or traditional semi-ring for the integers. So that previous formulation that we saw was called an SPL, or signal processing language formulation. SPL is the description stage of the Spiral code generation system. It defines computations over an implicit input X and stores the result in an implicit output Y. So as you can see from this table, we have a subset of the common SPL constructs that one could use during this formalization stage. So if we take, for example, the second construct, which does a tensor product of the identity matrix with a separate matrix A, this would just place the values of A along the diagonal into the output Y. And we can see that in code there on the right side of that table. So once we have that initial SPL expression that we got by the DAG system, we can then apply a rule tree to get an expanded SPL formulation, where this will utilize the library information, which describes, in more detail, the mathematical computation that's being performed. So the rule tree will take those descriptors and things that we had discussed and recognize that maybe the original formulation isn't getting performance because it's not utilizing some of those properties, and it'll give you a high performance variant instead. And the rule tree will understand that those two formulations are equivalent. So we originally had this try count expression, and then we're going to say, now we're going to do a column vector times matrix times row vector. That's the operation that the system has determined is best suited for that specific DAG. So once we now have the expanded SPL formulation, we want to provide our looping and access pattern information to actually carry out the operation. And this will be done the sigma SPL stage. So in this stage, there are four major constructs: the sum, the gather, the scatter, and the permutation. The sum is how you sort of loop over an expression. The gather is how you index into your input x. The scatter is how you index in your output y. And the permutation is sort of how you can permute the data during your computation. So if we take as an example, a scalar product, we can see the different stages that start on the left as our initial SPL formulation, then go to our expanded SPL formulation, then the sigma SPL formulation, and then finally the generated code. And again, with the expanded SPL formulation, what we're doing is we're doing a pointwise multiplication, which we're sort of writing out to our identity matrix and then composing that with a row vector of all ones to do the accumulation. And then this will be shown in sigma SPL with our gather and sum construct. So now we're using our gather to take an element from each of the two vectors that we're trying to perform the scalar product on, and we're going to compose that with our pointwise multiplication, and then we're in a sum for all the elements in the two vectors to actually do the accumulation and get our result. Yeah. So as you can see here, in order to move from the expanded SPL formulation given by our rule tree, we call a different rule tree called the sums rule tree, which will now do some further expansion to get our sigma SPL expression. So now we have our sums and our gathers and our scatters and things like that. One of the challenges with graph applications at the sigma SPL stage is the introduction of bilinear operations. So this is when an operation goes over two spaces and combines into a third space. Spiral did not cleanly support such operations, so we introduced a scoping object to do this. With the scope object, we define a variable that's responsible for going across and merging the two spaces into one space. So if we take, for example, again, our scalar product, we can see that it's a bilinear operation because we are going over the two distinct spaces, x0 and x1. Now through the scope object, we can bind x0 and x1 together and then use a variable to access both spaces and do that computation correctly and directly. And why the scope object was important is because it eliminates an issue with the generated code where you would store the values of the two vectors into a temporary array in one loop, and then you would compute over that temporary array in a separate loop. And that's not the canonical way one would write scalar product. You would just index into the two vectors as appropriate and do that computation all within one loop. So the scope variable allows us to do that canonical version of scalar product that we saw in the previous slide. So how the scope variable would be introduced is via a rewrite rule, which is sort of an expression modifier that is triggered in the event that certain properties are present in a formulation at any of the levels of the hierarchy, but in this case, the sigma SPL level. And specifically in this context, we have this gather of f stack underneath the sums rule tree, and that signifies the system that we're doing a bilinear operation because we have the stack of the two different vectors. And so what would happen is Spiral will understand that we have that property present, and it'll attach this scope object with the associated scope variable, SCPV here, in order to alleviate the code generation issue that would occur if it wasn't present. So this then sort of completed SPL expression would go through Spiral's basic block compiler, which utilizes its own intermediate representation called iCode. And at this stage, some classical compiler optimizations are performed, like dead code elimination. So and this is an optimization where statements that don't affect program results can be removed. So we have an if statement here that's always evaluating to true. So we're going to just remove the if statement and the associated else branch. We also have optimizations like copy propagation. And in this optimization, if you have an assignment y equals x, you can replace uses of y with uses of x as long as there are no intervening assignments to either x or y. So as you can see here, we have that y equals x and that 3 plus y use, but we don't actually change x or y. So we can just put x in place of y, and then through dead code elimination, we can actually remove y equals x. And then finally, we have optimization like array scalarization, which is given an array of length 1, you can just turn that into a variable instead. And then once all of these optimizations have been performed, this intermediate code is then translated to C code, which is outputted to a file. So we're going to go now through the end-to-end transformation that the spiral code generation system would go through. So it starts with the initial SPL formulation, which describes the computation that's being performed. And it does this by pattern matching our trace file DAG with known patterns. It'll then apply a rule tree, which uses expansion and backtracking techniques to discover these algorithmic optimizations and determine if a high performance algorithm exists that best makes use of carrier type information. From there, we need to add the addition of loops and access pattern information. And we do this via the sums rule tree and create our sigma SPL expression. And this sums rule tree will make use of this recursive descent, which will implement our SPL objects and expand upon them to give their looping equivalence. And it'll also use this term rewriting to modify expression if certain properties are present, like bilinearity, right? So then if those properties are present, it'll add things like the scope object to alleviate code generation challenges that might emerge, like a disconnected accumulation computation code loops. Finally, some classical compiler optimizations are performed on our intermediate representation. And then the intermediate representation is translated now to C code. Cool. So we compare our triangle counting implementation with the reference GBTL implementation, a hand-tuned implementation, and the multi-core implementation. We ran all these implementations on 2 data sets, a small graph with about 10,000 nodes and 25,000 edges, and a larger graph with about 20,000 nodes and 200,000 edges, without any sort of pre-sorting or modifications to the underlying data sets. So as you can see by our yellow and red bars, our code generation, generated code achieves performance that matches the hand-tuned, while additionally providing multi-core support for free using our tagging mechanism to the SPL expression. And I just want to make it clear at this stage that the goal of this system isn't necessarily to beat hand-optimized code, but rather to eliminate the need to rewrite library code to get performance. So we want to give performance that matches the state of the art, but we don't want to make developers rewrite their code. And in the event that the state of the art improves and new algorithms are created, we want to update our approaches to match those accordingly. So to more concretely illustrate some of the stages we discussed, let's look at a quick example of something that we all would understand, which is matrix multiplication from SPL to code. So when we launch Spiral, we first want to load our graph package that we saw and then configure our options for the specific code we wish to generate. So in this instance, I'm turning off dereferencing, I'm choosing instead to use this the conventional bracket access for arrays. And I'm also turning off global unrolling so that I can keep the relatively small loops intact, as we're just going to do a simple 3x3 matrix multiplication code generation. So from there, we will define our SPL formulation for matrix multiplication and apply a rule tree to get its expansion, which is just a call to the most basic matrix multiplication algorithm. And this computation is so simple that there really isn't much expansion at this stage. So from there, we can call our sums rule tree and introduce our sigma SPL loops and accesses, as well as our scoping object. And this is all sort of done directly on the fly. In this SPL expression, we have our 2 outer loops followed by our scope. And then so within the scope, we have this scatter, which we talked about how you index into your output. And within that scatter, we have this tensor product of the 2 F bases. And this is equivalent to accessing values in a flattened 2D array. So think of like 3, or in this case, 3 times I plus j. That's what that tensor expression would show, although it would be 3 times I5 plus I6 in this case. Then there is the scalar product, which has the accumulation of the BLK, and then followed by a gather just to index into our input x. And it follows the same tensor 2D array or flattened 2D array indexing scheme. And our scope variable there, T1 at the bottom. This then has our intermediate representation, or I code, and it looks something like this. And it shows in more detail the declaration of now we have our temporary variables and also our loops and assignments and things like, and as well as indexing and things like that into our expression. And then here we have the generated code from the intermediate representation. And I wanted to show side by side the effect that the scope variable had on our generated code. So if we see the expression on the left, we have this extra loop that's accumulating all the values for the matrix, the row and the column, into this temporary T2, and then doing the computation all within T2. But now, after we introduced our scope, we have it written in a more classical approach with just the 3 loops and some temporary variables that exist in between. So now let's say we wanted a version of matrix multiplication that used a mask. So this means that we're only really interested in some of the elements of our final result matrix, and we don't really care for the others. We don't want to do the computation for elements that are not in the mask. So we're going to again start with our configuration, but now we're going to provide an extra symbol to the options, which will generate an additional parameter to our function for the actual the mask matrix itself. We then pass our optional symbol to the mask SPL object, and then call our MXM with the mask as a parameter. We can then expand the SPL object and move into our expanded SPL formulation and our sigma SPL formulation. So in this sigma SPL formulation, we actually have to do a series of transformation stages in order to get the completed version that we would want. So in the beginning, our mask is merely composed with our triple loop matrix multiplication that we saw. And that's shown at the top with the mask times isum. What we'd like to do is move it inside the triple loop, and then we can query the mask to determine, should we compute for the valid element or not? So we first move that mask inside, and then we transform that mask to a sigma SPL conditional object, the con there, which checks if the element is valid in the mask, do the innermost loop, or otherwise, return 0. And we can see that by the scatter with the 0 matrix at the bottom. And this will result in the generated code that we see here, where now we have that if condition that exists to query whether the element we computed in the mask is valid or not. And what's nice about the construct that I've just described here is that Spiral doesn't really care about dense or sparse until actual generation of the code. So we can use many of these constructs, as you see here, but just replace them with their sparse representation, and then just generate the sparse equivalents instead. So we can do this for any kind of sparse data format, not just the CSR one, which I talked about a little before, but any of the other like CSC or DCSR or DIA, things like that. We can just define these as new constructs and then place them in, and Spiral will do the code generation, knowing that we have this construct in place of the original. So with the addition of new key features, the Spiral system now supports code generation for graph applications, as we see through our example of triangle counting. So we introduced sparsity to the Spiral system, which allows for sparse vector and matrix objects, as well as semi-rings in order to produce a sparse code. We can utilize DAGs in order to take from the trace file given by our library domain-specific language GBTLX the computation that's being performed, and then we can find an initial SPL expression that matches it. We do plan to extend this pattern matching to tag with additional architectures, and we can hopefully generating graph kernels for GPUs, FPGAs, and ASICs. We now cleanly support bilinear operations like matrix-matrix multiplication, which are the cornerstone of many of these graph applications, and allow for specifically that merged array accumulation computation code blocks. And the end result of this entire system is a write once, execute anywhere model, whereby the developer can describe their algorithm, and Spiral will generate code for either their local workstation or the largest supercomputer that's available today. Okay. So thank you. That's my references.